Hi.
We would like to introduce you, Abigail Flom, who's going to be presenting telescopic hydration observations of Chang'e 5 landing site in partial eclipse.
All right, thank you. All right, so the detection of a global 3 micron feature, as we all know, indicates hydration due to hydroxyl or water. However, in order to look at that feature, you have to remove thermal emission contamination. And there is disagreement by experts as to how to remove this thermal contamination. For moon mineralogy mapper data, there's at least 3 different methods for correction, and they provide conflicting predictions for the behavior of hydration on the lunar surface, as you can see in the plot on the right. So what we did to look at the Chang'e 5 site is I used the NASA infrared telescope facility to make observations between 1.6 and 4 microns, which goes out to longer, more thermally dominated wavelengths to help constrain this thermal correction. And we also exploited the changing temperature and illumination conditions before and during a partial eclipse. Partial eclipse is a helpful observation because the temperatures are reduced. The solar flux is also reduced, but by less than the thermal radiance is reduced. And therefore the thermal contamination at 3 microns is reduced. So we have observations from November 30th, 2020 UT, less than 24 hours before the Chang'e 5 landed on the moon. And so we have from throughout the partial eclipse, from 100% solar flux at about 365K to about 45% solar flux at around 300K. So for context, what we did is that red dot is the Chang'e 5 landing site, and we took a, we created a hyperspectral map using telescope data in that white box that you see outlined there. So when we look at the full illumination data, we do not see a decrease below the continuum around 3 microns, which indicates no hydration. However, when we look at our partial eclipse data set, we see a small decrease below the continuum, which could possibly be due to a hydration band. So we took a look at how this 3 micron band changes as you go to different illuminations. So as you can see at the higher illuminations, we see a higher 3 micron band ratio, which would mean no or less water. And then as we go to lower percent illuminations or deeper into eclipse with lower temperatures, then we see a lower 3 micron band ratio, which would indicate more hydration. If we take this 45% illumination case and we translate the 3 micron band into ppms of hydration, then around the Chang'e site, you can see around 50 ppm hydration, and at various other points in the map, as much as 150 ppm hydration. So having no hydration band in the full illumination data set is consistent with predictions from other studies like Lee and Millikan 2017 and Honeyball et al. 2020. However, the possible hydration band that we're seeing in partial eclipse is unexpected. So, you know, one possibility is that the hydration is changing during the eclipse. However, that would require either water to be migrating along temperature gradients, which is inconsistent with the upper exosphere limits by LADI, given the amount that we're seeing, or the temperature dependent formation of metal stable hydroxyl. However, we're in the magnetotail during eclipse, and we have been for days. So the timescale of hydrogen diffusion from solar wind is thought to be on the order of hours, not days. So that's a little strange. Then there's another possibility that we have to talk about, which goes back into correcting for thermal emission and how we're calculating reflectance. So the radiance that we measure is a combination of the reflectance times the photometric function and the solar radiance, plus the emissivity times the thermal emission model. And so if you assume Kirchhoff's law, which says that the reflectance plus the emissivity equals 1, then you can solve for reflectance, as you can see in that second bullet point, which is great, except when the denominator is 0. So if the solar radiance and the thermal radiance are equal, then you can't solve for reflectance. And so using this Kirchhoff's law assumption. And so this happened in our full illumination data set. So for the full illumination data, we had to use a thermal correction method that doesn't account for Kirchhoff's law. But if you have an emission feature and a reflectance feature being multiplied by the same radiance, then they can cancel each other out and it will look like 0. So at least for the full illumination data set, what's different might not be that the hydration has changed, but that our ability to measure it is different. And so this is a problem for that data set, and it's a problem for other places on the moon as well. And then as we go into the eclipse, the singularity isn't happening at 3 microns anymore, and we can see what's going on better. But before we sort of dismiss some data as not having the information that we need, we kind of need to look at the assumptions we're making. So in the thermal infrared, beyond the wavelengths that we are looking at now, Kirchhoff's law is known to not apply. And it's unknown if it applies at 3 microns. So, that's an assumption that Banfield made, that's an assumption that Lee made, that's an assumption we were making. So that's something that really needs to be checked if it's causing problems like this. The other thing is that every pixel that we look at has subpixel roughness. So, each facet has a different singularity wavelength and temperature, etc. So it may be that by accounting for subpixel roughness, even if the singularity is in the way, we might be able to find a solution where we can recover some of the reflectance information. So in the future, we're going to be looking at Kirchhoff's law's validity at 3 microns and addressing it. And in addition to that, for the Chang'e site, we have data collected from after the return launched. So we can compare that data to what was shown before landing as well, which will be really interesting. Thank you.
This is great. Thank you, Abigail.